convincing argument that they're independent. It's just there's Monte Carlo before doing the theorems, and I came up after like a little bit of walking and a little bit of math. I came up with a theorem which is going to be published elsewhere. So the derivation, we assume that they're uncorrelated or independent, but since we're talking about sort of Gaussian variables, which is about the same. We know that xy follows a variance gamma distribution. Actually, not very well known. Dilip Madan, who's mass finance, discovered that variance gamma distribution. It was a special case of some other distribution. And parameterize n over 2. And then, of course, the numerator is, the denominator is, as everyone knows, a chi-square distribution, which is that's standard. Now you want to see figure out the distribution of a variance gamma, a sum of variance gamma over a sum of chi-square distributed variable. So the product of two normalized Gaussian, as I showed, I pulled out the characteristic function, okay? And once you pull out the characteristic function, the proof here is that you take z, which is x minus y, x plus y, because if x is not Gaussian and y is Gaussian, x minus y would be a Gaussian variable, and s plus y would be a Gaussian variable, and they're both going to be independent. And from that, you get x squared minus y squared, which is basically the difference between two chi-squares. And that gives us a characteristic function, easy to work with. It's, of course, that you discover the variance gamma distribution, but also the sum stays within that distribution because visibly the sum is the sum is, in other words, you multiply the characteristic function to sum a random variable is going to be that of a variance gamma distribution, and it's very simple. That part is simple. A little bit of homework, heavy, and you pull out the distribution of that ratio. Now the equation above is quite fragile. You can rederive it for a specific n. You get very precise numbers. If you use this one, you got to take the limit. Instead of plugging in an n here, you got to take the limit of this heading towards that. So let me summarize. The regressions produce a lot of noise. That's stay in dimension one. When you go in high dimension, there's another problem. Produce a lot of noise. Never look at the numbers, just look at the graph. The graph, your eyes won't lie. I mean, they may lie somewhere, but not here. And good luck in debunking more nonsense by what I call that sinister racial psychologist program that is very active in the IQ domain and other characteristics. Thank you.
OK.
Alors, donc, voilà. Bonjour, chers amis. Là, on a Raphaël. Et comme on m'a demandé de faire une vidéo en français sur ce thème d'effet de portefeuille et d'ellipticalité, j'ai donc Raphaël qui veut dire un mot là-dessus.